Okay. Um, for this week's class, we're going to discuss sample size estimation. Basically, what is the appropriate sample size for a given survey or a poll? And the example we'll use is a poll published cited on CNN that was commissioned by NBC News Wall Street Journal. And in that poll, I'm going to focus on President Donald Trump. And in that poll of registered voters, 43% said they would vote for Donald Trump. Okay. Additional information on that report of that 43% saying yes, they would vote for Trump. I'm going to assume the opposite, 57% saying they would not vote for him. That was published by the NBC News Wall Street Journal, and it looks like the poll itself was commissioned, was run by Hart Research Associates. They were commissioned by NBC News Wall Street Journal to run it. As I can see here, they talk about the sample size was 900 registered voters. They give a little breakdown in terms of who they were in terms of cell phone and landline. And we're just going to focus on the 900. That's 900 registered voters were used to estimate the percentage of people, registered voters, who would vote for Trump. And what we're going to focus on is the margin of error. So the margin of error, as it says in the bottom box, for 900 interviews among registered voters is plus or minus 3.27%. So I'm going to focus on that part of this report, and that was for, once again, for the 43% saying yes, they would vote for Trump, accurate to within plus or minus 3.27%, 19 times out of 20. So we're going to discuss where that 3.27% comes from, and what is meant to the results being accurate to within plus or minus 3.27%, 19 times out of 20. Okay. So to step back, let's look at a much smaller sample size, not 900. Let's look at a sample size of 4. I'm going to have 4 respondents, and I'm going to ask the respondents, will you vote? Are you going to vote for Trump in the next U.S. presidential election? Yes or no? And the respondents are registered voters, and randomly sample. So I ask the first person, you going to vote for Trump? And they say yes or no. I'm going to assume, and I'll get to it later, a base within the population for all registered voters that it's a 50-50 split. There is a reason for this. It's not really what the true population proportion is, but it's the one I'm going to use to calculate the confidence interval. So I ask the first person, 50-50 chance they'll say yes, say no. And then call the next person, registered voter, 50-50 chance they'll say yes. This is my little probability tree, and if I go up the branch of each of this tree, it gives me a possible outcome at the termination of the branch. So the first one here is first person says yes, second person says yes, third person says yes, and the fourth person says yes. All 4 people said yes, they would vote for Trump. And that's a possible outcome if I call 4 registered voters and see if they'll vote for Trump or not. Each of these terminating branches represents a possible outcome. Next one is the first 3 say yes, the last person says no. Next one, first 2 say yes, third says no, and the fourth says yes. Each of the branches, they terminate into 16 possible outcomes. This list of outcomes, they're mutually exclusive, so there's no relationship between one or the other. These are just random events and I just go like, 0.5. And it's an exhaustive list. This is, if I ask 4 people whether they're going to vote for Trump, yes or no, they have to say yes or no. Then this is an exhaustive list of all possible outcomes. After the hyphen, I have a number, and that number represents the number who say yes, they would vote for Trump. So the first one, all 4 say yes. The next one, the first 3 say yes, and the fourth person says no. So that ends up 3 people. Similarly here, 3 people say yes, the first 2 and the last one, and the middle person said no. But what I'm focusing on is, at the end of the day, what I care about is 3 said yes, 1 said no. But there's different combinations of that can happen. And I can see of 3 people out of 4 saying yes, there's this outcome, this outcome here, and this outcome here. So I got 1, 2, 3, 4 possible outcomes where it is. 3 of them said yes, they would vote for Trump. 1 person said no. Okay. Now, these are all my possible outcomes. The probability associated with each outcome is I multiply probability up the branch, 0.5 for the first one. For all of them, actually, it's 0.5 for the first respondent, yes or no, 0.5 for the second, 0.5 for the third, 0.5 for the fourth. Multiply the probabilities up that path. It's 0.5 times by 0.5 times by 0.5 times by 0.5, which is 0.0625. Another way to look at it, I got 16 possible outcomes, each of equal probability. 1 over 16 is 0.0625. What I care about is the number of yeses in terms of the outcomes of sampling 4 registered voters. There's one outcome where the proportion is 1. And I mean by the proportion of Ys or yeses, all 4 people said yes, they would vote for Trump. Here, the proportion is 0.75. 3 out of 4 said they would vote for Trump. Here, 2 out of 4 said, which is 0.5. I'm now going to add up. All I care about is the proportions or the number of yeses. So I'm going to add up what proportion of the possible poll outcomes would lead to 75% saying yes, they would vote for Trump. So it's 0.0625 plus 0.0625 plus 0.0625 plus 0.0625. I can do that for 0 people voting, or 0.25, or 1 of 4 voting, 2 of 4 voting, 3 of 4 voting, and all 4 voting. And here that is on my next slide. So base probability is 0.5, say, and within the population, 50% vote yes, 50% vote no. Proportion yes. All 4 people voting for Trump, there's only one possible outcome, and that is, multiply up that path, 0.0625. I knew there were multiple times and there were 4 of them, where it was 75%, or 3 out of 4 would vote for Trump. I add up 3 times, the 0.0625, 4 times for each of the 4 outcomes, or 0.0625 times by 4 gives me 0.25. And similarly for 0.5, there's more of them. 0.5, there's 1, 2, 3, 4, 5, 6. So 0.0625 times by 6 gives me a probability of 0.3750 that I would get a sampling outcome where 50% said yes and 50% said no. If I look at this distribution here in a chart, I can see that it approximates very, very roughly the normal distribution. And I can also see, if I'm just ballparking it, that the mean for that distribution is 0.5. So on average, I would expect that the results of my poll would be 50% say yes, I would vote for Trump, 50% would say no. So nice here. It's only a sample size of 4, but it does roughly, very roughly approximate the normal distribution. And as my sample size gets larger, this distribution here more closely approximates the normal distribution. Okay. Back to our original study. The sample size was 900. I need a metric that will give the reader a sense of my level of confidence in the accuracy of my poll result. And we refer to that as a confidence interval. Now, to work with this and to calculate my confidence interval, I have to do slightly more advanced, trickier probability calculations. And to ease those calculations, what I do is I'm going to use the standard normal curve to calculate cumulative probabilities. And the cumulative probability that I want to know is, I want to know the cutoff from that normal distribution, the cutoff for the bottom 2.5% of possible outcomes, which would be 0 voting yes, saying yes, 1 saying yes, 2 saying yes, up to whatever that cutoff is out of the 900 who say yes. So I want the cutoff for the bottom 2.5%, which would be the 0.25% percentile, and I also want the cutoff for the top 2.5%. which would be the 97.5 percentile. So my metric is going to be tell me what the outliers are in terms of possible poll outcomes for the bottom 2.5%. Tell me the probability of an outliers that are in the top 2.5%. And it follows this here, but it's just expanded out from not, this is 0, 1, 2, 3, 4. It'd be 0 out to whatever these proportions are, out for 900. And I want to know from that big normal curve, what's the cutoff for the bottom 2.5%? What's the cutoff for the top 2.5%? And I know in between those boundaries, the boundary between the bottom 2.5% and the top 2.5%, in between is everything else. And that represents 95% of the possible outcomes in terms of the survey outcomes in terms of proportion to say yes, they would vote for Trump. And that's referred to as the 95% confidence interval. The 95% confidence interval is the possible outcomes that are within the boundaries that cut off the bottom 2.5% and the top 2.5%. And everything in between represents the 95% confidence interval. Now, to do that for a sample size of 900 and calculate those really percentiles or those proportions, I'm going to use a standard normal curve, and I need, for any standard normal curve, I have to calculate a z-score. I can do this because for that binomial distribution, a binomial distribution, and assuming it's 0.5, and another reason to assume it's 0.5 because it is actually normally distributed for 0.5, the population proportion is equal to p, which is 0.5, as I see here from my little example. And Q is 1 minus p. So the proportion p is those who say yes, I assume it's 0.5. Q is the proportion who say no, they won't vote for him, which is 1 minus p, which is 0.5. And then the standard deviation for that distribution is the square root of PQ over N. Having a mean, a standard deviation, I can then calculate the cutoff for the bottom 2.5% and the top 2.5%. And to do that, I need to use the standard normal curve. Okay, so my unknown is going to be what that cutoff is, which is x over n, which will be a proportion. So whatever it is, 43 out of I don't know, out of 900 or whatever it is. Say 400 out of 900 or something. I want this proportion right here. That's going to be my unknown, but I'm going to need the z-score. That's the cutoff for the bottom 2.5% and the top 2.5% from the standard normal curve. And I can see here that in the table I use, that cutoff is a z-score of plus or minus 1.96. So for any normal distribution, and then using the standard normal curve and the z-score calculation, a z of negative 1.96 will be the cutoff for the bottom 2.5%, and the z-score for equal to 1.96 is the cutoff for the top 2.5%. So that's what I'm going to do. So I know this value here is plus or minus 1.96. I know this value here, P is 0.5, Q is 0.5, and N is 900. And I know that this value is 0.5. I'm going to solve for x over N. Okay, here's the calculation. Standard deviation is 0.5. It's 0.5 times by 0.5 divided by 900. Take the square root of that, which gives me a value of 0.01667. Here are the z-scores, which I talked about before, the plus or minus 1.96. Solve for that. It's anchored to the assumed true population proportion of 0.5. The cutoff for the bottom 2.5%, that cutoff is 46.3% or fewer voting for Trump. The cutoff for the top 2.5% is 53.27% or more voting for Trump. So if I get a sample that says that 55% voted for Trump, that would be in the top 2.5%. Conversely, if I get a poll result where it says that 45% voted for Trump, that would be in the bottom 2.5%. So those are my cutoffs. Okay. If I take the difference, here's the cutoff for the bottom 2.5%, and I subtract that from the assumed population value of 0.5, which I used for the Z-score calculation, that value is minus 0.0327. If I take the cutoff for the top 2.5%, subtract from it 0.5, that gives me plus 0.0327. That matches the confidence interval that the Harris Research Associates reported. They say their margin of error for 900 interviews among registered voters is plus or minus 3.27%. So what they're saying is the result bounded between minus 3.2% and plus 3.2%, that represents the boundary that cuts off the bottom 2.5% and the top 2.5%, and everything in between is 95% of all possible outcomes. Okay, so the plus or minus 0.0327 or 3.27% is referred to as the 95% confidence interval. The poll results reveal that 43% of registered voters would vote for Trump. The results of the poll are accurate to within plus or minus 3.27% 19 times out of 20. This means that if I ran the poll 100 times, so I just ran this poll 100 times, and my sample size for each poll is 900. So I run it 100 times, and for each of those 100 times, I have 900 registered voters in a sample. The true population mean would be within the plus or minus 3.27% boundary for approximately 95% of those 100 polls. For 5 of the polls, the true population percentage would be outside of the plus or minus 3.27% boundaries. So I can say, okay, my result was 43%, accurate to within 3.27%, plus or minus 3.27%, 19 times out of 20. The 19 times out of 20, if I times that by 5, that gives me 100 out of 100, and that's 95 out of 100. They just kind of like shrink it down to 19 times out of 20. But 19 times out of 20 represents 95 out of 100. So I can say, okay, results are 43%. My metric for my level of confidence, or my feeling of how accurate my results are, is to say that 95% of the time, my results will be accurate to within plus or minus 3.27%. Now the question is, for the given result, and you have to throw out the window of the 0.5 now, because I only use, I'll explain why we use it in a sec, but just throw that out the window. I don't know what it is. It's kind of like behind the curtain. I've only assumed it's 0.5 for reasons I'll explain in a sec. If I throw that out the window, I'm going to anchor that plus or minus 3.27% to the 43. So I'm going to take 43% and then plus or minus 3.27% from that 43, which would give me approximately a boundary of between 39.25 and 46.27. Right? Those are boundaries. And I'll say my results are accurate within the plus or minus 3.27%, 19 times out of 20. Is the true population mean within those boundaries? And my answer is, I don't know. All I know is, you know what, if you ran this thing 100 times, 95, I'd have a different polling result for probably each of the 20 times. But for 19 of those times, if I said, okay, here's the boundaries for the plus or minus 3.27% for that given poll result, whatever it is, the true population mean will be within those boundaries. Do I know whether that's the case for my poll? I don't know. All I can just say is, run it 100 times, 95 times out, it will be within the 95% confidence, within that plus or minus 3.27%. 5% of the time, 2.5% of the time will be lower than 3.27%. 2.5% will be higher than the plus 3.27%. I just don't know for my given example. But it does give me an indicator of the level of accuracy of my polling results. And we'll get to that right now. The key driver in this is the denominator of the z-score, which is the standard deviation. As n gets larger, this value here gets smaller and smaller. And at the end of the day, when I solve for x over n, as this value gets smaller, it's a smaller fraction or value when I multiply it by the 1.96. So if this value gets smaller, I'm basically, the plus or minus from the 0.5, it's a smaller value. Meaning that the larger the n, so once my n gets larger, this value here gets smaller and smaller, meaning a tighter confidence interval. So here is, and seeing that here, as the sample size gets larger, my confidence interval gets smaller and smaller. The denominator here in this fraction gets smaller. Now, I can see here, our result was accurate to within plus or minus 3.27, sample size of 900. To get an accuracy of plus or minus 3.25%, I need a sample size of 909. So that's a close approximation. But what I can see here is that kind of like as my confidence interval gets smaller, as my sample size gets larger, it gets more costly. So, to get to roughly 3.25% roughly means about 900. But if I want to go down to 2.5%, which was plus or minus 2.5%, I need a sample size of roughly almost 1,600. So it's I basically have to increase my sample from 900 to 1,500 to shave off 1 percentage point in my confidence interval. Now, comparison of sample sizes, assuming the base proportion is 0.5 versus the base proportion is 0.1. When I use 0.5, my confidence interval for a given sample size is the confidence interval is widest when for a base proportion of 0.5. So here's 0.5 here. To get to a 3.2 plus or minus 3.25% was 909 here. It was 909 here. The sample size is much smaller if I assume that the base proportion is 0.1. So when I use 0.5, it creates the largest denominator, and which then inflates out the confidence interval. So I always go with plus or a base assumed proportion of 0.5 because it generates the widest confidence interval. It produces the largest or the largest denominator, right? So if I have a base proportion of 0.5 and a sample size of 900, my confidence interval is 0.0327. And that produces the largest denominator. If I take that down to 0.1, that means my confidence interval for a sample size of 900 is not plus or minus 3.27%. It's actually plus or minus 1.9%. So since I don't really know what the true proportion is in the population, if I assume 0.5, it gives me the most conservative estimate of what the confidence interval is. So I'm just being conservative. Pick as an assumption a base proportion of 50-50, 0.5, p equal to 0.5, because it gives me the most conservative or the highest estimate of what the confidence interval truly is. And that is the end of our recording.